Okay, let's unpack this. Welcome to the Deep Dive.
Great to be here.
We're the show that plunges into complex topics,
Yeah.
well, distills them into essential, engaging insights. We really want to give you that shortcut to being truly well-informed.
That's at the goal.
And today, we're diving into the absolutely fascinating, often invisible, yet utterly fundamental world of metals.
It really is fundamental, isn't it?
Just think about it for a moment. From the tiniest microchip components, nestled inside your phone, to the colossal beams that give skyscrapers their breathtaking height. Metals are, quite literally, the backbone of our modern lives. They are everywhere, constantly at work, supporting, conducting, enduring.
Can't escape them.
Yeah, exactly. Yet how many of us truly understand what's happening beneath their often shiny surfaces? How do they acquire their incredible strength, or their surprising malleability, or maybe their remarkable resistance to wear and tear?
It's a hidden world for most people.
That's precisely where we come in today.
And what's fascinating here, what makes this deep dive maybe a bit different, is our source stack.
Right. It's not the usual research paper this time.
No, not a sprawling article.
Yeah.
Instead, we have something perhaps even more profound in its own way. A comprehensive glossary of terms related to metals.
A glossary. Which, okay, might sound a bit dry at first.
It might, but before you imagine us just reciting definitions, let me tell you. This isn't merely about memorizing words.
Okay.
Each term in this glossary is like a precise interconnected doorway. When we unlock these doors, we start to reveal the intricate processes, the unique properties, the profound phenomena that define metallic materials.
So treasure trove, really.
It is. It lets us go beyond just knowing what something is to understanding how it works and, crucially, why it matters.
Exactly. And that's our mission today.
Yeah.
To transform what might initially seem like dense technical definitions into clear, engaging insights that genuinely empower you, the listener.
Giving you that understanding.
We're providing that shortcut, allowing you to become truly well-informed about metallurgy, the science of metals, without needing to pore over heavy textbooks for weeks.
Hopefully making it a bit more accessible.
We're going to uncover some surprising facts, I think, highlight the incredible interconnectedness of these concepts, and most importantly, continuously answer that crucial question for you. Why should you care?
Because you interact with these materials constantly.
Right, because once you understand the hidden lives of metals, the materials that build our world, you'll see the objects around you in a whole new, much more appreciative light. So let's begin by looking at the very building blocks themselves.
Makes sense. Start at the beginning.
Kicking us off with the most fundamental question. What is metal, really, at its core? And what truly happens when you start combining them, moving beyond just a single, pure element?
Okay, fundamentally, a metal is defined by its atomic structure, specifically how its outermost electrons behave. They aren't tightly bound to individual atoms, they're sort of delocalized, forming what scientists often call a sea of electrons.
A sea of electrons.
Okay. And this unique metallic bonding is what gives metals their characteristic properties. They're typically good conductors of electricity and heat. They're ductile, meaning you can draw them into wires.
Like copper wire.
Exactly. And they're malleable. You can hammer them into thin sheets. Think gold leaf. Plus, they usually have that distinct luster, that shine.
Got it. But then you start mixing them.
Ah, yes. That's where it gets really interesting. That's where alloys come in. An alloy is essentially a substance that still has metallic properties, but it's composed of two or more chemical elements. Critically, at least one of those elements must be a metal.
So metal plus something else.
Usually metal plus another metal, or metal plus a non-metal in smaller amounts. And the real magic, the purpose of alloying, is that the resulting substance usually possesses qualities that are quite different and often vastly superior to its individual components.
So you're engineering the properties.
Precisely. You alloy to enhance specific things. Maybe you want more strength, better corrosion resistance, a different melting point, or even just to make it easier to machine.
Can you give an example?
Sure. Think about gold jewelry. Pure gold, 24 karat, is actually quite soft. Too soft for everyday wear.
Right. It would scratch easily.
Exactly. So you alloy it, typically with copper or silver or other metals, to create 18 karat or 14 karat gold. It's still gold, looks like gold, but it's much stronger, more durable. It's like material alchemy, really.
That's fascinating, this idea of material alchemy. You mentioned chemical elements. It's always struck me as surprising how something seemingly simple and, well, non-metallic like carbon plays such a transformative role, especially when you add it to iron.
Ah, carbon, yes.
I've even read it's treated metallurgically almost as if it were a metal itself. That seems quite a distinction for a non-metallic element. How does that work?
You're absolutely right. Carbon's role is central, particularly in the world of steels. Chemically, yes, it's a nonmetal, no question.
Okay.
But in metallurgy, its behavior and the profound impact it has on the internal structures and properties of iron. Well, it means we handle it and think of it in terms of being an alloying element.
Even though it's not a metal.
Correct. Because just a tiny percentage of carbon, sometimes less than 1%, can radically change iron's characteristics. It goes from being relatively soft iron to much harder steel.
That small amount makes such a difference.
A huge difference. And that leads us to differentiate between types of steel. For instance, alloy steel is specifically defined as steel containing significant quantities of alloying elements beyond the common amounts of carbon, manganese, silicon, sulfur, and phosphorus that you find in plain carbon steel.
So alloy steel has extra ingredients besides the carbon.
Exactly. Elements like chromium, nickel, molybdenum, vanadium. These are added along with precisely controlled carbon levels to tailor the steel for specific demanding jobs.
Like what?
Oh, incredible toughness for armor plate, maybe extreme wear resistance for cutting tools, or the ability to withstand high temperatures in jet engines, things far beyond what plain iron or simple carbon steel could ever achieve.
And it all comes down to how those tiny carbon atoms fit in.
It fundamentally does. It's about how carbon atoms, being much smaller than iron atoms, can kind of wedge themselves into the iron's atomic lattice structure. That distortion is key.
So we're really talking about elements at the atomic level here, aren't we? Can you break down how these atoms arrange themselves? This lattice thing sounds important. Why is that precise arrangement so critical?
Absolutely critical. The very foundation of any solid metal is how its atoms are arranged in space. Imagine stacking oranges in a crate. There are specific repeating ways you can stack them efficiently.
Okay, like in neat rows and layers.
Exactly. A crystal is essentially a physically homogeneous solid where the atoms or ions or molecules are arranged in a specific, highly ordered three-dimensional pattern that repeats over and over again.
Like a microscopic scaffolding.
That's a great way to put it. And this precise repeating scaffold is what we call the crystal lattice. Now, while there are actually only 14 basic types of these lattices possible in nature, the subtle variations within these and how different elements fit into them define a metal-specific internal structure.
14 basic types, that's surprisingly few.
It is, but they combine in many ways. The critical point here is that even slight changes at this atomic level, like introducing a carbon atom into an iron lattice, as we discussed.
Right.
Or even just a shift in temperature, causing the atoms to rearrange into a different stable lattice pattern. These changes can dramatically impact the macroscopic properties we see and use.
Like hardness or conductivity.
Exactly. It dictates everything. How light reflects off the surface, giving it luster, how it deforms under stress, its ductility or brittleness, how effectively it conducts heat or electricity. It is the fundamental blueprint for the metal's behavior.
That's the atomic level, truly the invisible architecture. But when we look at a piece of metal, maybe under a powerful microscope, what are we actually seeing? How do we visualize these internal structures? Because it's definitely not just a uniform block, is it?
Not at all. What you see when you magnify a metal surface properly is its microstructure. This is the structure we observe on polished and, importantly, etched metal and alloy specimens. Etching uses chemicals to selectively reveal the details.
Why etching?
Because etching attacks different parts of the structure like grain boundaries or different phases at slightly different rates. This creates contrast, making the structure visible under a microscope, typically at magnifications over 10 times life size, often much higher.
So you see, what, like little regions?
You see individual grains, which are crystals oriented differently. You see the boundaries between these grains. And if it's an alloy, you see the different phases present and any distinct constituents within that alloy. A constituent is simply any micrographically distinguishable part of the alloy structure.
Okay, so distinct features within the overall pattern.
Exactly. And to capture these incredible details, we use techniques like photomicrography or micrography. These are essentially just highly magnified photographs of the metal's internal grain structure.
And why are these pictures so important?
They are invaluable for scientists and engineers. They provide a direct visual link between the processing the metal underwent, like heat treatment or casting, and its resulting internal architecture. And that architecture, as we said, determines its properties. It's diagnostic.
Right. And when it comes to iron and steel, which are so common, there are specific phases or maybe secret identities that iron can shift between depending on temperature and carbon content.
Yes, precisely. Iron is fascinatingly polymorphic.
These phases sound absolutely crucial for understanding steel's behavior. Can
Yeah.
you walk us through the main ones? Because it feels like understanding these transformations is the key to unlocking steel's versatility.
You're absolutely right. This is foundational for steel, arguably our most important engineering material. Iron, remarkably, can exist in several distinct crystal structures or phases, each with profoundly different properties.
Okay, let's hear them.
First, at room temperature and up to about 1670 degrees Fahrenheit or 910 Celsius, we have alpha ferrite. This is the body-centered cubic, or BCC, form of pure iron. It's relatively soft, ductile, and importantly, it's magnetic. Think of it as the normal state of iron.
ECC, body-centered cubic, okay.
Then, if you heat iron above that 1670 degree Spurgrack, its crystal structure rearranges. It transforms into austenite, also known as gamma iron. This is a face-centered cubic, or FCC, structure.
Okay, FCC, different arrangement.
Different arrangement. And austenite is unique because it can dissolve a much larger amount of carbon compared to ferrite. This is absolutely critical for heat-treating steel. Also, austenite is non-magnetic.
So that's why some steels are magnetic and others aren't.
It's a major reason. Austenite is the key phase we aim for when heating steel for hardening, because it gets the carbon into solution. Now, an austenite steel is one that contains enough specific alloying elements like nickel or manganese to keep that stable austenitic FCC structure even when cooled down to ambient temperatures. Many stainless steels fall into this category. They're often non-magnetic, very corrosion-resistant, and quite ductile.
Okay, ferrite, austenite, what else?
Next, we have martensite. This is a truly remarkable and very important microstructure. It's formed by what's called a diffusionless phase transformation.
Diffusionless, meaning atoms don't move far.
Exactly. Imagine the atoms rearranging almost instantaneously, kind of shearing into a new configuration without needing time to diffuse or travel much within the structure. This happens when you cool austenite incredibly rapidly quench it.
So super fast cooling.
Very fast. Martensite is the key constituent found in hardened steel. It's famous for its needle-like or plate-like microstructure, and it's incredibly hard, but often quite brittle. There's also alpha martensite, which represents an initial, less developed, highly strained stage in this rapid transformation.
Hard but brittle. That sounds like a trade-off.
It is, which we'll get to.
Yeah.
Then there's cementite. Its chemical formula is F3C iron carbide. It's not a phase of pure iron, but a distinct compound of iron and carbon with its own orthorhombic crystal structure.
Iron carbide.
Right. And cementite is extremely hard and brittle. Its presence, how much there is, and how it's distributed within the steel structure is absolutely critical for determining the steel's overall hardness and wear resistance.
So it adds hardness.
Significantly. Now, ferrite can also be used as a more general term. It refers to any solid solution where one or more elements are dissolved in the body-centered cubic BCC phase of iron or steel. It's the predominant phase in what we call ferritic steels. These, as the name suggests, are mostly ferrite, so they're magnetic and often have good ductility and formability.
Okay, so similar to malphaferrite, but can have other things dissolved in it.
Precisely. And finally, one more crucial one. Tempered martensite. Remember we said martensite is hard but brittle?
Yes.
Well, you almost always follow hardening with tempering. Tempered martensite is what you get when you take that hard, brittle martensite and gently reheat it to a temperature below the critical transformation range. Hold it for a bit, then cool it.
Why do that?
This reheating allows for some subtle atomic rearrangement. It forms body-centered cubic iron, like ferrite, but with a very fine dispersion of tiny iron carbide particles. This process is vital because it significantly improves the toughness and impact strength of the steel, making it much less brittle, while still retaining a large portion of the hardness gained from quenching.
So you get the hardness and toughness.
That's the goal. It's a difference between a razor blade that snaps easily and a sword that holds a sharp edge but can also withstand the shock of impact.
So these are all distinct forms the iron and carbon can take within the steel,
Right.
and they have really different properties. How do they relate to these transformation concepts I hear about, like eutectic or eutectoid reactions? That sounds very scientific.
They are deeply connected. Those reactions are the specific mechanisms, the recipes by which these phases form or transform into one another, usually triggered by precise temperature changes and compositions.
Okay, break it down.
Let's start with protectoid. This simply refers to a constituent, like ferrite or cementite, that separates out of a solid solution before the main eutectoid reaction occurs during cooling. It forms first, in a sense.
Okay, forms earlier.
Now, for the main events, eutectic and eutectoid. They sound similar, but there's a key difference.
Okay.
A eutectic reaction is an isothermal, meaning it happens at a constant temperature and reversible reaction, where a liquid solution, a molten mixture, decomposes upon cooling into two or more distinct, intimately mixed solids.
Liquid to solids.
Yes. Imagine cooling a specific liquid alloy composition. At one precise temperature, the entire remaining liquid solidifies simultaneously into a fine mixture of two solid phases. This composition has the lowest melting point in that part of the phase diagram. It's crucial for casting alloys.
And eutectoid.
A eutectoid reaction is also isothermal and reversible, but critically, it involves a solid solution converting into two or more intimately mixed solids upon cooling.
Solid to solids.
Exactly. The most famous example is in steel. Austenite, a solid solution, cools down, and at a specific temperature, around 133 degrees A for Rosser or 723 degrees C for plain carbon steel, transforms into a mixture of ferrite and cementite, often forming a layered structure called perlite.
Ah, so that's how ferrite and cementite can form together.
That's a primary way. Both eutectic and eutectoid reactions are fundamental for understanding how alloys solidify and how their microstructures develop, which in turn dictates their properties. They involve reaching a state of equilibrium, a dynamic balance where atomic movements are happening, but there's no net change in the overall phase composition. They are the bedrock principles for designing alloys and heat treatments.
So if I'm interacting with metal components every day, maybe building something, using a tool, driving a car, why is understanding these internal structures, these minute, almost invisible transformations, so absolutely critical? What does this all mean for me?
It's critical because these internal structures and the way they transform directly dictate almost every useful property of the metal. Its strength, its hardness, its toughness, its ductility, its corrosion resistance, how it behaves under heat or stress.
This is not just academic.
Not at all. If you need a super strong wear-resistant steel for, say, a gear or a cutting tool, you need to engineer the heat treatment to produce a specific microstructure, probably involving martensite and carbides.
Right.
If you need a ductile, easily formable sheet metal for stamping out car body panels, you're aiming for a different microstructure, maybe predominantly ferritic or perhaps austenitic for some stainless steels.
Okay.
Predicting how a metal component will respond to the forces it encounters in service, whether it's constant load, sudden impact, high temperatures, vibration, or a corrosive environment, all hinges on understanding this internal architecture and knowing how it was created through alloying and thermal treatments.
So without this knowledge,
Without it, material selection and design would be just guesswork. And when you're building bridges, airplanes, surgical implants, or pressure vessels, well, guessing is simply not an option. It's the fundamental science that ensures safety, reliability, and performance. It's the difference between a product that works flawlessly for its intended lifespan and one that could fail unexpectedly, potentially catastrophically.
that makes perfect sense. It
Okay.
really underscores the precision involved. We've talked about the internal makeup, the atomic dance. Now let's transition. How are metals actually given their initial physical form? And how do we start controlling those characteristics right from the beginning? This often starts with turning molten metal into solid shapes, right?
Yes, the most fundamental way we shape metal from its liquid state is through casting. In essence, you pour molten metal into a mold cavity that has the negative shape of the part you want, let it cool and solidify, and then remove the solid metal part.
Sounds simple, but I bet it's complex.
Oh, immensely. Many factors are critical. One key property of the molten metal itself is its fluidity. That's its ability to flow easily and completely fill all the intricate details of the mold cavity before it starts to solidify.
How do you measure that?
There are specific tests. A common one is the spiral casting test, where you see how far the metal flows down a long spiral channel in a standard mold. There are also more complex molds, sometimes called a Chinese puzzle, designed to assess flow through tricky pathways.
Okay. And the molds themselves, what are they made of?
Molds can be made from various materials, but sand is very common, especially for ferrous metals like iron and steel. The mold components are quite intricate. You typically have a flask, which is the rigid metal or wooden frame that holds the compacted sand mold. It usually comes in two parts. The top half is the cope, and the bottom half is the drag.
Cope and drag, got it.
Inside the flask, the actual mold cavity is formed by packing sand around a pattern. The pattern is a model of the part you want to make, often made of wood, plastic, or metal.
The positive shape.
Exactly. If the part is complex, the pattern might be a parted pattern made in 2 or more pieces so you can remove it from the sand without wrecking the cavity. And patterns need pattern draft.
Draft, like a breeze.
No, like a taper. It's a slight angular taper applied to the vertical surfaces of the pattern. This allows the pattern to be withdrawn cleanly from the compacted sand mold without pulling sand away with it.
Makes sense. What about hollow parts?
For hollow sections or internal features, you use a core. This is a separate preformed shape, usually also made of sand, that gets placed inside the main mold cavity before pouring. The molten metal flows around it, creating the internal void.
So the core shapes the inside.
Precisely. Cores are made from specialized core sand mixed with a core binder, a sort of adhesive that holds the sand grains together and gives the core strength to withstand the molten metal. Critically, cores must also have core vents.
Vents.
For air, for gases. When hot metal hits the binder in the core, gases are produced. These vents are small holes or channels that allow these gases to escape easily from the mold. If they get trapped, they cause defects like blowholes in the casting.
Right, trapped gas bubbles.
Exactly. And finally, the molten metal doesn't just get dumped in. It flows through a carefully designed gating system. This is the whole network of channels that directs the metal smoothly into the cavity.
Like plumbing for liquid metal.
Kind of. It includes the sprue hole, where you pour the metal in, usually vertically, the runners, horizontal channels distributing the metal, and the gates, the specific entry points into the actual part cavity. And very importantly, there's usually a riser.
A riser? What's that for?
A riser is a reservoir of extra molten metal connected to the casting cavity. As the metal in the main casting cools and solidifies, it shrinks. The riser acts like a reserve tank, feeding liquid metal back into the casting to compensate for this shrinkage, preventing voids or shrink defects.
So it keeps it topped up as it solidifies.
Exactly. Risers can be open risers, extending right through the top of the mold and open to the air, or blind risers, which are completely enclosed within the sand but might have a small vent.
Wow. That's a remarkable number of components and precise steps just for one mold.
Mm-hmm.
And I assume there are different types of casting processes too, not just sand.
Oh, absolutely. The specific casting process chosen is a huge decision. It depends on the metal being cast, the size and complexity of the part, the required surface finish and dimensional accuracy, and of course the number of parts needed the production volume.
So what are some main types?
Well, sand casting is one of the oldest, most versatile, and still widely used methods, especially for larger parts in ferrous metals. The mold is made from, well, sand, usually silica sand.
Right.
This sand can be used as green sand, which is a mixture of sand, clay as a binder, and water. It's used while still damp or green. Or you can use a dry sand mold, where the mold is baked to remove all moisture before pouring. This makes the mold stronger and more stable, good for heavier castings.
Green sand versus dry sand. Okay.
Foundries might also use facing sand, which is a finer, specially prepared sand mixture placed right against the pattern surface to give the final casting a smoother finish. Controlling the sand properties, what's called sand control, is vital. You monitor its fineness, permeability, how easily gases pass through, green strength when damp, moisture content. Finding the optimum moisture is key.
Lots to manage just with the sand.
It is, and increasingly, foundries use sand reclamation processes to clean and reuse the sand, which is better environmentally and economically.
Makes sense. What else besides sand?
For parts needing high precision and intricate detail, investment casting is fantastic. It's often called lost wax casting.
Lost wax.
Yes, because you start with an expendable wax pattern, an exact replica of the part made of wax. This wax pattern is then dipped repeatedly into a ceramic slurry. The first coat is often a very fine slurry called a dip coat to capture fine details and ensure a smooth surface.
Okay, coating the wax.
Right. You build up a ceramic shell around the wax pattern. Then you heat the whole thing gently, usually below 250 degrees F, 121 degrees C, in a process called dewaxing, to melt out the wax.
Hence lost wax.
Exactly. What's left is a hollow ceramic shell mold with incredible detail. You then fire this shell to strengthen it and pour the metal into it. It's great for complex shapes like turbine blades or jewelry.
Very precise. Any others?
Centrifugal casting is a really interesting one. Here, the mold is rotated at high speed while the molten metal is poured in.
Spun around. Why?
The centrifugal force pushes the molten metal firmly against the outer walls of the mold. This creates very dense sound castings free from porosity, especially good for cylindrical shapes like pipes, tubes, or sleeves.
Makes sense. The force pushes it outwards.
Right. It's also used for bimetal or dual metal centrifugal casting. You can pour one metal, let it partially solidify against the mold wall, and then pour a second different metal inside it. The centrifugal force fuses them together, creating a layered component with potentially different properties on the inside and outside.
Like a wear-resistant lining inside a tougher shell.
Exactly that kind of thing. Machines are categorized by their axis of rotation. Horizontal axis for long parts like pipes. Vertical axis for shorter, ring-like shapes.
Clever.
Yeah.
What about really high-volume parts?
For high volume, especially with non-ferrous metals like aluminum, zinc, or magnesium alloys, die casting, or pressure die casting, is dominant. It uses reusable steel molds called dies.
Reusable molds.
So, molten metal is forced into the die cavity under very high pressure. The dies are usually water-cooled, so solidification is rapid. It allows for extremely fast production rates, excellent dimensional accuracy, and very smooth surface finishes. Think about intricate automotive parts, electronic housings, things like that.
High speed, high precision.
Yes, but mostly limited to lower melting point non-ferrous alloys because the steel dies can't withstand molten steel temperatures repeatedly. And one more specialized one, vacuum casting.
Casting in a vacuum.
Essentially, yes. The melting and pouring happen under very low atmospheric pressure. Why? To remove dissolved gases from the molten metal, which can cause porosity, and to prevent oxidation during melting and pouring. This results in extremely clean, high-integrity castings, often used for critical aerospace or medical applications where purity is paramount.
The sheer ingenuity behind just shaping raw metal from a liquid state is truly incredible. So what does this all mean when you're holding a cast metal part? Maybe it's a complex engine block or even just a simple bracket.
It means that every single feature of that part, its overall shape, any internal cavities, the texture of its surface, its basic dimensional accuracy, is a direct result of the specific casting process chosen and how well it was executed. It dictates the part's initial grain structure, its soundness, freedom from defects like pores or cracks, its surface finish, and even some of its initial mechanical properties. The choices made during casting the mold type, the gating design, the pouring temperature, the cooling rate are absolutely fundamental to the final product's integrity and how it will perform later on. It's the critical first step in transforming a raw liquid into a solid, functional component ready for its next stage, which is often heat treatment.
Okay, so we've got our metal in its initial solid form, maybe shaped by casting, maybe by forging or rolling. But as you said, that's often just the beginning. How can we then further alter or enhance the metal's inherent properties after it's solidified? This is where I imagine heat comes back into play in a big way, like that second act of alchemy you mentioned.
Precisely. This brings us squarely into the realm of heat treatment. And it is arguably one of the most powerful tools in the metallurgist's toolkit. It's defined as a precisely controlled combination of heating and cooling operations applied to a metal or alloy in its solid state, specifically to produce desired properties and microstructures.
So manipulating the solid structure with heat.
Exactly. It really is like alchemy, but it's grounded in a deep understanding of those phase transformations we talked about, controlling atomic arrangements through temperature and time.
What's a common example?
One of the most common is annealing. Generally, annealing involves heating the metal to a specific temperature, holding it there for a certain time, called soaking, and then cooling it at a controlled rate, which is usually slow, like letting it cool down in the furnace.
And the purpose of annealing?
The main goals are usually to soften the metal, making it easier to machine or form, to increase its ductility, to relieve internal stresses induced by previous processing, or to refine the grain structure for better uniformity and toughness.
So making it more workable or stable?
Generally, yes. There are specialized types, too. For example, bright annealing. This is annealing carried out in a controlled furnace atmosphere, maybe an inert gas like nitrogen or argon, or even a vacuum. The point is to prevent the metal surface from oxidizing or scaling during the high-temperature process, so it comes out bright and clean.
Useful if the surface finish matters.
Very, especially for things like stainless steel sheets or tubing. And for certain steels, particularly hypotectoid steels, those with less carbon than the eutectoid amount, there's double annealing. This is a two-step process. Heat high, cool rapidly, then reheat to a lower temperature and cool slowly. It's used to get a finer, more refined grain structure than a single anneal might achieve.
Okay, so annealing is mostly about softening and refining. What's the opposite? That's where you get that legendary hardness in things like tools or knives, right?
Exactly. The opposite of slow cooling is rapid cooling, which we call quenching. This typically involves heating the steel into the austenite phase region where carbon dissolves, then cooling it very rapidly, usually by immersing it in a quenching medium.
Like water or oil?
Yes, those are common. Water provides a very fast quench. Oil is a bit slower and less severe. You can even use forced air for some highly alloyed steels that's air quenching. The speed of the quench is absolutely critical to achieve the desired transformation, usually to get that hard martensite phase.
But rapid cooling sounds like it could cause problems, like warping.
It absolutely can. Rapid, uneven cooling induces significant internal stresses and can cause distortion or even cracking. That's where a clever technique called interrupted quench, or more specifically mart-tempering, comes in.
Mart-tempering, how does that work?
With mart-tempering, you quench the part from the austenitizing temperature into a bath held at a temperature just above the start of the martensite transformation range, often a hot oil or molten salt bath. You hold it there just long enough for the entire piece to reach that bath temperature, equalizing the temperature throughout its cross-section.
Okay, equalize the temperature. Then what?
Then you remove it from the bath and allow it to cool relatively slowly, usually in air, through the martensite transformation range. Because the temperature is uniform before this final cooling, the martensite forms more gradually and uniformly throughout the piece, significantly reducing internal stresses, distortion, and the risk of quench cracking, while still achieving a fully martensitic, hard structure.
So hardness without the extreme stress. Very smart.
It is. Now, beyond just quenching for martensite, there are various other ways to achieve hardening. One important mechanism is age hardening, also sometimes called precipitation hardening or artificial aging if done above room temperature.
Age hardening. Does it harden over time?
Yes, essentially. It applies to specific alloys, like certain aluminum, copper, or nickel alloys and some steels. You first heat treat them to create a supersaturated solid solution, then quench them. After quenching, either at room temperature over time, natural aging, or more commonly by reheating moderately, artificial aging, extremely fine particles of a second phase precipitate out within the metal structure. These tiny precipitates act like roadblocks to dislocation movement, making the alloys significantly harder and stronger.
So tiny particles forming inside make it harder.
Exactly. Then there's induction hardening. This is a surface hardening technique.
Just hardening the surface.
Right. You use high-frequency alternating magnetic fields generated by an induction coil placed near the surface of a steel or iron part. These fields induce electrical currents, eddy currents, within the surface layer, rapidly heating just that layer into the austenite range.
Super fast surface heating.
Very fast, very localized. As soon as it reaches the right temperature, the power is shut off, and the surface is immediately quenched, usually by spraying it with water or oil. This creates a very hard, wear-resistant martensitic layer on the surface, while the core of the part remains softer and tougher. It's great for shafts, gears, axles.
Things that need a tough core but a wear-resistant skin.
Oh, precisely.
And that leads us to the broader category of case hardening. Induction hardening is one type, but case hardening generally refers to any process that produces a surface layer, or case on a ferrous alloy, like steel, that is substantially harder than the interior, or core.
Why do that? Why not make the whole thing hard?
Because often you need a combination of properties. You want extreme surface hardness for wear resistance, but you also need the core to be tough and resistant to fracture under impact or bending loads. Making the whole part super hard often makes it too brittle. Case hardening gives you the best of both worlds.
Okay. What are other ways to case harden besides induction? Several important methods involve changing the chemistry of the surface layer by diffusing elements into it at high temperature. Carburizing is perhaps the most common.
Adding carbon.
Exactly. You heat a low-carbon steel part in a carbon-rich atmosphere, like carbon monoxide gas or packed in charcoal. Carbon atoms diffuse into the surface layer. After enough carbon has soaked in, you quench the part. The high-carbon surface layer transforms to hard martensite, while the low-carbon core remains softer and tougher.
So you enrich the surface with carbon first.
Yes. Similar is carbonitriding, sometimes called nicarbing. Here you diffuse both carbon and nitrogen into the steel surface simultaneously, usually from a gaseous atmosphere containing both ammonia and a carbon source.
Carbon and nitrogen, both.
Nitrogen, like carbon, hardens steel. It also helps the steel harden more easily during the quench, improves hardenability, and can be done at slightly lower temperatures than carburizing. It produces a hard, wear-resistant case.
Okay, and nitriding.
Nitriding is another surface hardening process, but it relies solely on diffusing nitrogen into the surface of special alloy steels. containing elements like aluminum, chromium, molybdenum that form hard nitrides. You heat the steel part in an atmosphere of ammonia gas or in contact with nitrogen-bearing salts.
Just nitrogen this time.
Right. Nitrogen diffuses in and reacts with the alloying elements to form extremely hard, stable nitride particles directly in the surface layer. A key advantage of nitriding is that it's often done at lower temperatures than carburizing or carbonitriding, and crucially, no quenching is required afterwards to achieve hardness.
No quenching. That's a big deal for distortion, isn't it?
Huge deal. Nitriding produces an extremely hard, wear-resistant, and fatigue-resistant case with minimal distortion, making it ideal for precision parts like crankshafts, gears, and tooling.
It's incredible how much precise control you have over the material just by manipulating temperature, time, atmosphere, and cooling rates. Are there other vital heat treatments that are critical for different properties beyond just hardening or softening?
Oh yes, several others are absolutely fundamental for fine-tuning material properties and ensuring reliability in service. We already mentioned tempering, which is almost always done after hardening steel to martensite.
Right, to reduce brittleness.
Exactly. You reheat the hardened steel, but importantly, to a temperature below its lower critical transformation temperature, where it would start turning back to austenite. The higher the tempering temperature, the softer but tougher the steel becomes. It's a critical trade-off adjustment. Its main goal is significantly improving impact strength and toughness.
Making it less likely to shatter.
Precisely. And sometimes, especially for highly alloyed steels or tool steels, you need double tempering.
Tempering twice. Why?
Because after the first quench, some austenite might remain untransformed, trapped in the structure. This is called retained austenite. During the first tempering cycle, this retained austenite might decompose, forming fresh, untempered, and brittle martensite upon cooling. The second tempering cycle is then needed to temper this newly formed martensite, ensuring a uniform, tough final structure.
Catching any leftover transformation.
Okay. Another common treatment is normalizing. This involves heating a ferrous alloy, like steel, to a suitable temperature above its upper transformation temperature, AC3, holding it to ensure it's fully austenite, and then cooling it back down, typically just in still air.
Cooling in air, how is that different from annealing?
Annealing usually involves much slower cooling, often inside the furnace. Air cooling is faster than furnace cooling, but slower than quenching. Normalizing produces a microstructure that's generally harder and stronger than annealed steel, but not as hard as quenched steel. Its main purpose is to refine the grain size, make the structure more uniform, reduce internal stresses from prior work, like forging, and improve machinability and toughness compared to the as-rolled or as-forged condition.
So a middle ground for refinement.
In a way, yes. Then there's homogenizing. This is a high-temperature heat treatment often applied to castings or ingots soon after they solidify.
Homogenizing, making it more uniform.
Exactly. When alloys solidify, especially large sections, the different elements don't always distribute perfectly evenly. You get microscopic variations in composition called segregation. Homogenizing involves heating the alloy to a very high temperature, holding it for a long time, to allow diffusion, atomic movement, to occur and essentially stir the elements around, reducing these chemical variations and making the composition much more uniform throughout the part. This leads to more consistent properties.
Smoothing out the chemical lumps, so to speak.
A good analogy. And finally, a really crucial one for reliability is stress relieving.
Relieving stress. Sounds therapeutic.
For the metal, it is. Manufacturing processes like casting, uneven cooling, welding, machining, or cold working, like bending or drawing, can introduce internal stresses within the metal. These are called residual stresses.
Stress is locked inside the part.
Yes, even when there's no external load applied. These residual stresses can be harmful. They can cause distortion or warping over time or during subsequent machining. They can lower fatigue life, and they can make the material more susceptible to stress corrosion cracking.
So you want to get rid of them?
You do. Stress relieving involves heating the component to a moderate temperature, below the transformation range so you don't alter the main microstructure, holding it long enough for the metal to relax internally through microscopic plastic flow, and then cooling it slowly and uniformly to avoid introducing new stresses. It's vital for dimensional stability and long-term performance of many components.
Here's where it gets really interesting for me.
Yeah.
The sheer level of control required for all of this. How precise do the temperatures and the cooling rates actually need to be for these treatments to work effectively? And what happens if you get it was just slightly wrong? Because it sounds like a very delicate dance.
It is a delicate dance, and the precision required is often paramount. We're talking tight temperature tolerances, sometimes just plus or minus 10 or 20 degrees Fahrenheit, and carefully controlled heating and cooling rates. Even slight deviations can dramatically alter the resulting microstructure and properties.
Oh, so?
Take quenching, for example. There's a critical cooling rate for any given steel. That's the absolute minimum rate of continuous cooling required to bypass the formation of softer phases, like perlite or bainite, and transform the austenite entirely into the desired hard martensite. If your cooling rate falls even slightly below this critical value, perhaps because the part is too large or the quench isn't effective enough.
You don't get full hardness?
Exactly. You'll end up with a mixed microstructure, softer and less wear-resistant than intended. The part might fail prematurely in service.
And that relates to the size of the part, doesn't it?
Absolutely. That's the mass effect. The sheer size or mass of a component significantly influences the actual cooling rate achieved internally during heat treatment, even if the surface is cooled rapidly.
The inside cools slower than the outside.
Always. Larger, thicker sections simply cannot dissipate heat as quickly as thinner sections. This means that even with an aggressive quench, the core of a large part might cool slower than the critical cooling rate, resulting in a softer core compared to the harder surface. This variation in properties across the cross-section needs to be accounted for in design.
So mass effect limits how deep you can harden something.
Essentially, yes, especially for plain carbon steels. Alloying elements are often added specifically to reduce the critical cooling rate, allowing thicker sections to be hardened more effectively. We call this increasing the hardenability.
Okay. And what if you get the heating part wrong? Too hot, perhaps?
That can also be disastrous. A metal can be overheated if it's exposed to an excessively high temperature during heat treatment or held there for too long. This causes the grains within the microstructure to grow excessively large.
Big grains are bad.
Usually, yes. A coarse grain structure generally leads to lower toughness and ductility, making the metal more brittle. The good news about overheating, however, is that the damage is often not permanent. It can sometimes be corrected by subsequent heat treatment, like normalizing, or by mechanical working, like forging, to re-refine the grain structure.
Okay, so overheating is fixable sometimes. What isn't?
A burn structure. This is far more severe. Burning occurs if the metal is heated to such an extremely high temperature, often close to its melting point, that irreversible damage occurs. This usually involves incipient melting or severe oxidation at the grain boundaries.
Melting at the boundaries.
Yes, even if the bulk doesn't melt. This permanently weakens the cohesion between the grains. A burn structure cannot be fixed by heat treatment. The material is essentially ruined, often brittle and useless. It's cooked beyond repair.
A very fine line, then, between optimal heating and burning.
It can be. And controlling these processes precisely relies on understanding concepts like equilibrium, that state of dynamic balance between atomic movements where the net change in phases is zero under specific conditions and kinetics, like isothermal transformation.
Isothermal transformation.
That's the process of transforming austenite into other phases, like perlite, bainite, or martensite, not by continuous cooling, but by rapidly cooling it to a specific temperature within the transformation range and holding it there at that constant temperature until the transformation is complete. Diagrams called TTT, time temperature transformation, curves map out these isothermal transformations and are crucial tools for designing specific heat treatment cycles to achieve desired microstructures.
So it all comes back to controlling time and temperature with incredible precision.
Absolutely. These are the scientific principles that underpin all successful, predictable heat treatments.
So what does this all mean for us, the listener? Thinking about the metals all around us, does it mean that they aren't static, unchanging materials, but rather their properties are dynamic, meticulously engineered through these incredibly complex, highly controlled processes? It sounds like an ongoing, intricate design project for every single part.
That's precisely the takeaway. Metal properties are not just inherent fixed characteristics that you're stuck with. They are dynamic, flexible, and can be and are meticulously tailored for specific applications.
Tailored how?
Through the entire journey. Selecting the right elements to create an alloy, controlling the solidification during casting or forming, and then applying these precise, carefully managed heat treatments. We can engineer specific microstructures at the atomic and microscopic level.
And those microstructures determine the final performance.
Exactly. They yield desired macroscopic properties, whether that's extreme strength for a tool, remarkable ductility for a car panel, outstanding toughness for a bridge component, or exceptional hardness for a bearing. It highlights the immense scientific and engineering effort that goes into virtually every metallic component we rely on.
So it's not just metal, it's engineered metal.
It's engineered metal. It's a testament to how understanding and controlling these phase transformations and microstructural changes allows us to unlock a metal's full potential, ensuring it performs reliably and safely in its intended role, often for decades, sometimes under incredibly demanding conditions.
That transition from just a lump of raw material to a precisely engineered component is truly amazing. It's like, I don't know, turning simple clay into a specialized, high-performance ceramic through firing. Okay, let's shift gears again. We've talked about creating the structure. Now let's talk about the character of these materials once they're made and put into service. How do metals actually behave under stress, under constant force, or when exposed to different environmental conditions? What are their inherent limits, and how do we measure them?
Right. This brings us to the crucial domain of mechanical properties and performance characteristics. These are the numbers and concepts engineers use to select materials and design parts that won't fail.
So how strong is it? How much can it take?
Exactly. The most fundamental measure of strength often is tensile strength, or more precisely, ultimate tensile strength, UTS. This is the maximum stress a material can withstand while being pulled or stretched in tension before it fractures.
The breaking point when pulling it apart.
Essentially, yes. It's calculated by taking the maximum load achieved during a tensile test and dividing it by the original cross-sectional area of the test specimen. It tells you the peak pulling force it can handle.
But parts usually shouldn't break, right? They just shouldn't deform permanently.
Correct. And that's where yield strength comes in. Yield strength is the stress at which the material begins to deform plastically, meaning it undergoes permanent deformation. Before this point, it stretches elastically and springs back when the load is removed. After the yield point, it stays deformed.
So yield strength is the limit for permanent bending or stretching.
Precisely. It's often a more critical design parameter than tensile strength because you usually want components to return to their original shape after being loaded. Sometimes, particularly in low-carbon steels, you see a distinct upper yield point, which is a clear peak stress right before yielding begins, often followed by a slight drop in stress as plastic deformation starts.
And that region before yielding is the elastic region.
Yes. The elastic limit is technically the maximum stress a material can withstand without any permanent deformation upon release of the load. And elasticity itself is just that fundamental property of a material to recover its original shape and size after a deforming force is removed.
But if you go beyond the elastic limit,
you enter the realm of plastic deformation. That's permanent distortion, stretching, bending, compressing that remains after the load is removed.
Okay, how do we quantify how stiff a material is, how much it resists stretching even elastically?
That's measured by the modulus of elasticity, also widely known as Young's modulus. It's the ratio of stress to the corresponding strain, the amount of deformation, specifically within the elastic limit.
Stress divided by strain.
Right. It's a measure of the material's stiffness or rigidity. A higher modulus means the material stretches less under a given load. For most carbon and low alloy steels, Young's modulus is remarkably consistent, around 30 million pounds per square inch, PSI, or about 207 gigapascals, GPa.
30 million CSI, that sounds stiff.
It is quite stiff compared to many other materials like aluminum or polymers. There are other related moduli, too. The modulus of resilience measures the amount of energy a material can absorb elastically per unit volume up to its yield limit. Think of it as the energy storage capacity before permanent deformation.
Okay.
The modulus of rigidity, G, or shear modulus, relates to how a material resists twisting or shearing forces. It's the ratio of shear stress to shear strain in the elastic range.
For twisting motions.
Yes. The modulus of rupture is a value calculated from bending tests, flexure or torsion twisting tests. It's not a true material property like Young's modulus, but rather an index of the material's strength under those specific loading conditions calculated based on the load at fracture.
An indicator of breaking strength in bending or torsion.
Right. And the modulus of toughness represents the total energy absorbed per unit volume by the material up to the point of fracture. It includes both the energy absorbed elastically and the energy absorbed during plastic deformation. It's essentially the area under the entire stress-strain curve.
So, a measure of how much energy it takes to break it completely.
Exactly. We also talk about cohesion, which is the fundamental force holding the atoms or particles together within the material. And for forces pushing on the material, we perform a compression test to determine its compressive strength, yield, the maximum compressive stress it can handle without permanent deformation or buckling.
That's a comprehensive look at how they react to direct, steady forces. But metals often face other challenges, right? What about resistance to damage that builds up over time or failure under specific environmental conditions? That seems like where the real long-term challenges lie.
Absolutely. Those time-dependent and environment-dependent failure mechanisms are critically important for durability and safety.
Like hardness. How does that fit in?
Hardness is a crucial property, generally defined as a material's resistance to localized plastic deformation, usually by indentation or scratching. It's not the same as strength, but often correlates with wear resistance.
How is it measured?
There are several standard tests. The Brinell hardness number, BHN test, uses a large tungsten carbide ball pressed into the surface with a specific load. The Rockwell test uses either a small steel ball or a diamond cone, depending on the scale, and measures the depth of indentation under load. The Vickers test uses a square-based diamond pyramid indenter and measures the size of the indentation optically. Each gives a hardness value on its own scale.
Different ways to measure resistance to indentation.
Yes. There's also the Meyer hardness test, which is interesting because it involves making indentations with different loads and analyzing how the hardness changes. It gives an indication of the material's tendency to work hardened to get harder as it's deformed plastically. And the simpler Mohs scale is just a comparative scratch hardness scale using 10 standard minerals from talc 1 to diamond 10.
Okay, what about sudden impacts, like dropping something heavy on it?
That's where impact strength or impact value comes in. It measures a material's ability to withstand sudden, high-rate loading a shock. It's usually expressed as the amount of energy absorbed in fracturing a standardized test specimen in a single blow.
How do you test that?
The most common method is the Charpy impact test. It uses a pendulum hammer that swings down, strikes, and breaks a small, notched specimen. The energy absorbed by the specimen during fracture is measured by how high the pendulum swings up afterwards. Often, a standard keyhole specimen with a specific notch geometry is used, as notches concentrate stress and make materials more susceptible to brittle fracture, especially at low temperatures.
So it measures toughness under shock loading.
Exactly. Now, one of the most insidious and dangerous failure modes, especially for parts subjected to repeated loading like axles, springs, or rotating machinery, is fatigue.
Fatigue? Like getting tired?
In a way, yes. Fatigue is the gradual weakening and eventual fracture of a material under repeated or fluctuating loads, even if the maximum stress applied in each cycle is well below the material's static yield strength or tensile strength.
So it fails even though it was never overloaded in one go.
Precisely. It's a progressive failure. A fatigue crack or failure typically initiates at a microscopic stress concentration point, like a tiny flaw, inclusion, sharp corner, or even just a surface scratch. This tiny crack then grows incrementally with each load cycle.
Slowly spreading.
Yes. The fracture surface of a fatigue failure often shows characteristic markings sometimes, like concentric seashells or beach marks that trace the crack's slow progression, followed by a final rougher area where the remaining cross-section broke suddenly when the crack got too large.
How do engineers deal with fatigue?
They design based on the material's fatigue limit, or endurance limit, which is the maximum stress level below which the material can supposedly withstand an infinite number of load cycles without failing, though not all materials have a true infinite limit. Or they design for a specific fatigue strength, which is the stress level the material can withstand for a specific finite number of cycles, say 10 million cycles, before failure is expected. Understanding fatigue is absolutely critical for preventing unexpected failures in things like aircraft structures or engine components.
Makes sense. What about slow deformation over time, especially when it's hot?
That phenomenon is called creep. It's the slow, gradual plastic deformation of a material that occurs over long periods when it's subjected to a constant stress, particularly at elevated temperatures, even if that stress is below its normal yield strength at that temperature.
So it slowly stretches or sags under load when hot.
Exactly. Think of turbine blades in a jet engine operating at high temperatures under centrifugal force, or pipes in a power plant carrying hot steam under pressure. They can slowly elongate or bulge over time due to creep. The creep limit is defined as the maximum stress a material can withstand for a specified time at a given temperature without exceeding a certain amount of deformation or without rupturing. Designing against creep is crucial for high-temperature applications.
Okay. And you mentioned toughness before. How is that formally defined?
Toughness is a really important concept, but a bit complex. It's fundamentally the ability of a material to absorb energy and deform plastically before fracturing. It's a measure of resistance to crack propagation.
So not just strength, but resistance to breaking.
Yes. A material can be very strong, high yield strength, but brittle, low toughness, meaning it fractures easily once a crack starts. Another material might be slightly less strong, but much tougher, meaning it can deform significantly and absorb a lot of energy before it breaks. Toughness isn't a single value. It depends heavily on factors like temperature. Many materials become brittle when cold. The rate of loading, faster loading, often reduces toughness, the size of the part, and critically, the presence and sharpness of notches or flaws.
So toughness is context dependent.
Very much so. And failures can be broadly classified by how much deformation occurs. A brittle fracture is one that occurs with little or no noticeable plastic deformation. It's often sudden and catastrophic. In contrast, a ductile fracture involves significant plastic deformation before breaking. Sometimes you see a crystalline fracture or granular fracture, which describes a fracture surface that looks rough or granular, showing the facets of the individual crystals or grains, often characteristic of brittle failure in metals.
Are there specific things that can make metals brittle unexpectedly?
Yes, several environmental or processing-related factors can cause embrittlement. Hydrogen embrittlement is a major one.
Hydrogen getting into the metal.
Exactly. Metals, especially high-strength steels, can absorb atomic hydrogen during processes like electroplating, welding, pickling, acid cleaning, or even from exposure to certain corrosive environments. This absorbed hydrogen significantly reduces the metal's ductility and toughness, making it susceptible to delayed, brittle fracture under stress, sometimes well below its normal yield strength. Acid embrittlement is a similar phenomenon, specifically related to hydrogen pickup during acid cleaning.
Hydrogen is bad news for toughness.
Very bad news. Another issue is temper brittleness. This occurs in certain alloy steels, particularly those containing chromium, nickel, manganese, along with impurities like phosphorus or antimony, when they're held within or cooled slowly through a specific temperature range, roughly 850-1100 degrees Fif or 450-600 degrees Ceta during or after tempering.
So slow cooling after tempering makes them brittle.
In this specific temperature range, yes. It causes a significant drop in toughness, especially noticeable in notched bar impact tests performed at room temperature or below. It's a reversible phenomenon, but needs careful control of cooling rates after tempering for susceptible steels.
Okay. What about just general degradation from the environment? Rust, for example.
That falls under corrosion. Corrosion is the gradual destruction or deterioration of a material, usually a metal, by chemical or electrochemical reaction with its environment. Rusting of iron is the classic example of electrochemical corrosion.
And it can happen in different ways.
Yes. One particularly dangerous form is intergranular corrosion. This is corrosion that occurs preferentially along the grain boundaries within the metal.
Eating away at the glue between the crystals.
Essentially, yes. It can severely weaken the material from the inside out, sometimes with little visible damage on the main surface, making it very insidious and hard to detect before failure. We sometimes use a corrosion index, which is a calculated number expressing the maximum depth corrosion would penetrate in 1 year under specific, defined conditions as a way to compare materials or environments.
Okay. What about physical damage from rubbing or scraping?
That's wear. Wear is the undesired damage or removal of material from a component's surface due to mechanical action. There are different types. Abrasion is wear caused by hard particles or protuberances sliding or rubbing against the surface, things sandpapering. Frictional wear, or adhesive wear, occurs when two surfaces slide against each other, causing material transfer and detachment. Pitting is the formation of small cavities or pits on the surface, which can be caused by various mechanisms, including surface fatigue under repeated contact stress, localized corrosion, or cavitation in fluids.
So wear is physical removal of material.
Right. And sometimes corrosion and stress combine in nasty ways. Stress corrosion cracking, SCC, is a spontaneous failure mode where cracks initiate and grow in a susceptible material under the combined action of tensile stress, either applied or residual, and a specific corrosive environment.
So the stress and the corrosion work together to cause cracking.
Exactly. Neither the stress alone nor the corrosive environment alone would cause failure, but together they can lead to sudden, brittle fracture, often at stresses well below the yield strength. It requires a specific combination of alloy, environment, and stress state.
That sounds hard to predict.
It can be very challenging. And speaking of stress, those internal stresses or residual stresses we mentioned earlier, the ones locked in from manufacturing, they play a huge role here as they provide the tensile stress component needed for SCC, even if there's no external load.
Right. What about temperature changes causing failure?
Yes, rapid temperature cycling can lead to thermal fatigue. The repeated expansion and contraction as the material heats and cools induces cyclic stresses that can eventually cause fatigue cracks, just like mechanical fatigue. And thermal shock is the severe stress developed if a material is heated or cooled extremely rapidly and unevenly. If the stress exceeds the material's strength, it can crack instantly. Think of pouring cold water onto a very hot glass dish.
Okay. And finally, just reacting with air.
That's oxidation, the reaction of an element or compound with oxygen. For metals at high temperatures, this often leads to scaling. Scales are those relatively thick, often partially adherent layers of oxidation products that form on the surface. A common example is the dark mill scale, mostly iron oxides, that forms on steel surfaces during hot rolling or forging. This scale usually needs to be removed before subsequent processing, like painting or plating.
Wow. Okay, that's a lot of ways a metal can degrade or fail. So what does this all mean for you, the listener? Why is selecting the right metal for the right job, considering all these potential failure modes, absolutely critical? And why does understanding this prevent catastrophic events in the world around us?
It means that designing anything with metal, whether it's a simple tool, a complex machine, or a massive structure, requires a deep understanding of these potential failure modes. Engineers don't just choose a metal based on its initial strength or cost.
They have to think about the long term.
Exactly. They meticulously analyze the entire life cycle. What forces will it experience? Will they be steady or cyclic? Fatigue. What temperatures will it operate at? Creep, thermal fatigue. What environment will it be exposed to? Corrosion, SCC, embrittlement. How resistant does it need to be to wear or impact?
It's a complex balancing act.
It is. They must select a material with the optimal combination of properties: tensile strength, yield strength, toughness, hardness, fatigue resistance, creep resistance, corrosion resistance for that specific application. And they design the component's shape and features to minimize stress concentrations and mitigate risks.
And understanding how things fail helps prevent it.
Absolutely. Understanding these failure mechanisms, fatigue, creep, brittle fracture, SCC, corrosion, is the absolute difference between creating a reliable product or structure that performs safely for its intended lifespan and designing something that could fail prematurely and catastrophically. Think bridges, aircraft, pipelines, medical implants. The consequences of failure can be immense. This knowledge is the scientific and engineering foundation for ensuring safety, reliability, and building trust in the technology and infrastructure that surrounds us.
That's a really powerful point. Ensuring trust through understanding failure. Given all these potential failure modes and the intricate internal structures we discussed earlier, how do we actually ensure the quality and integrity of these complex materials, especially when flaws or defects might be hidden, not immediately visible to the naked eye? This sounds like a job for some incredibly advanced technology.
You're absolutely right. Visual inspection alone is often insufficient. This is precisely where the field of non-destructive testing, or NDT, sometimes called NDE, non-destructive evaluation, comes into play.
Non-destructive, meaning you test it without damaging it.
Exactly. NDT comprises a wide range of techniques that allow us to inspect or test a component for flaws, defects, or material characteristics without impairing its future usefulness. It's like giving the metal part a thorough medical checkup, x-rays, ultrasounds, etc., without needing surgery.
What are some common NDT methods?
One widely used method, especially for ferromagnetic materials like steel and iron, is magnetic particle inspection, MT.
How does that work?
You first induce a magnetic field in the part. If there's a surface or near-surface discontinuity like a crack, it disrupts the magnetic field, causing some of the magnetic flux to leak out at the surface. Then you apply fine ferromagnetic particles, iron filings essentially, either dry or suspended in a liquid carrier. These particles are attracted to the flux leakage areas, accumulating directly over the flaws and forming a visible indication, making even very fine cracks easy to see.
Clever. Using magnetism to reveal cracks. What about non-magnetic materials like aluminum or some stainless steels?
For surface-breaking flaws in both non-magnetic and ferromagnetic materials, Liquid penetrant testing, PT, or dye penetrant testing is very common.
Liquid penetrant.
Yes. You apply a special liquid, called a penetrant, to the clean surface of the part. This liquid has very low surface tension and high capillary action, so it seeps into any cracks, pores, or other discontinuities that are open to the surface.
Okay, it soaks into the cracks.
Right. After allowing sufficient dwell time for penetration, you carefully remove the excess penetrant from the surface. Then you apply a developer, usually a fine white powder suspended in a volatile solvent or applied dry. The developer acts like blotting paper, drawing the penetrant trapped in the flaws back out to the surface by capillary action.
And that makes the flaw visible.
Exactly. The penetrant, which is often brightly colored, usually red or fluorescent, glowing under UV light, stains the developer, creating a visible indication directly above the flaw, often much wider than the flaw itself, making it easy to detect.
Good for surface flaws. What about finding problems inside the material?
For internal flaws, ultrasonic testing, UT, is a powerhouse technique. It uses high-frequency sound waves, typically in the range of 0.5 to 20 megahertz, far above human hearing.
Sending sound waves into the metal.
Yes. A probe, called a transducer, sends pulses of ultrasonic waves into the material. These waves travel through the material until they encounter a boundary or discontinuity like the back wall of the part, or an internal flaw such as a crack, void, or inclusion.
And the waves bounce back.
They do. They reflect or refract off these interfaces. The transducer then detects these returning echoes. By analyzing the time it takes for the echoes to return and their amplitude strength, technicians can determine the location, size, and nature of internal flaws with remarkable accuracy. It's like sonar for materials.
Amazing.
Yeah.
Any other internal methods?
Eddy current testing, ET, is another important one, particularly good for surface and near-surface flaws in conductive materials, and also for measuring things like coating thickness or material sorting.
Eddy currents.
Yes. You use a probe containing a coil of wire carrying an alternating electrical current. This creates an alternating magnetic field around the coil. When you bring the probe close to a conductive material, like metal, this magnetic field induces circulating electrical currents within the material itself. These are the eddy currents.
Okay, currents induced in the part.
Right. These eddy currents, in turn, generate their own magnetic field, which opposes the original field from the coil. Any defect or change in the material's properties, like conductivity or permeability or geometry, like a crack or thinning near the surface, will disrupt the flow pattern of these eddy currents. This disruption changes the impedance, electrical resistance, of the coil in the probe. By monitoring these changes in impedance, the instrument can detect flaws or variations. It's very fast and sensitive for surface-breaking cracks.
Okay, and X-rays. Like medical X-rays.
Exactly like medical X-rays in principle. X-ray inspection or industrial radiography uses penetrating radiation, X-rays or gamma rays, to create images of the internal structure of objects.
How does that work for metal?
The radiation passes through the object being inspected and strikes a detector, which could be photographic film or a digital detector array. Areas where the material is thicker or denser will absorb more radiation, appearing lighter on the resulting image, radiograph. Areas that are thinner, or where there's a void or a less dense inclusion, like slag, will absorb less radiation and appear darker. This allows you to visualize internal voids, porosity, cracks, if oriented favorably, inclusions, and even assembly details. Microradiography is a specialized version using fine-grained film or detectors to achieve very high magnification of the radiograph, revealing fine details of microstructure or segregation.
Seeing right through it. What about getting really close-up views of the structure?
For extremely high magnification and detailed imaging of surfaces and microstructures, the scanning electron microscope, SEM, is indispensable. It doesn't use light. It uses a highly focused beam of electrons scanned across the specimen's surface.
Electrons instead of light.
Yes. Various signals are generated as the electron beam interacts with the surface atoms, secondary electrons, backscattered electrons, X-rays. Detecting these signals allows the SEM to build up incredibly detailed images with very high resolution, down to nanometers, and a large depth of field, giving a 3D-like appearance. It's fantastic for examining fracture surfaces, fractography, to determine failure modes, or analyzing microstructural features in great detail.
Seeing things at the nanoscale.
Pretty much. And if you want to know the elemental composition of tiny features seen in the microscope, you can use microspectroscopy. This technique often uses a focused electrical arc or laser beam to vaporize a microscopic area of the sample, and then analyzes the light emitted its spectrum to identify the specific metallic elements present in that tiny spot.
Identifying materials at a micro level. Amazing tools. Now, that's great for detecting hidden flaws in a finished part. But what about problems that occur specifically during the casting process itself? Are there typical defects that foundry workers or engineers doing quality control are actively looking out for right after a part comes out of the mold, even before NDT?
Oh, absolutely. Casting, as we said, is complex, and preventing defects during solidification is a primary focus. There's a whole catalog of common casting defects that visual inspection or simple checks can often reveal immediately, signaling problems with the process.
Like what kind of things?
One common surface defect is a cold shut. This looks like a crack or seam on the casting surface, but it usually has smooth, rounded edges. It happens when two streams of molten metal flowing through the mold cavity meet but are too cold or sluggish to fuse together properly.
So they didn't fully merge.
Exactly. Similar defects are cold lap, which appears as wrinkled or folded markings on the surface, where a thin layer solidified and was then covered by more molten metal without fusing, and cold shot, which are small, solid globules or spheres of metal that got splashed during pouring and became embedded in the casting but aren't fully joined to it.
All related to metal being too cool or flowing poorly.
Generally, yes. Then there are defects caused by trapped gas. Blowholes are irregular-shaped cavities, usually with smooth walls, found inside the casting or sometimes breaking the surface. They're caused by gas bubbles getting trapped as the metal solidifies.
Where does the gas come from?
It can be air that was mechanically entrapped during turbulent pouring, gases generated from the moisture or binders in the sand mold or cores when hit by hot metal, or even gases, like hydrogen, that were dissolved in the molten metal itself and came out of solution during solidification. A blister is a specific type of shallow blowhole right near the surface, often covered by just a thin skin of solid metal.
Trapped gas bubbles. Okay. What about shrinkage? You mentioned risers help prevent that.
Yes, but if the risering isn't adequate or the feeding isn't effective, you get shrink defects, also called shrinkage voids or cavities. These occur because most metals contract, decrease in volume when they transition from liquid to solid. If there isn't enough extra liquid metal fed in from the riser to compensate for this volume loss as the last parts solidify, a void forms.
So an empty space where metal should be.
Right. These can be large, concentrated cavities, or they can be spurred out. Dispersed shrinkage refers to small, scattered shrinkage cavities often found near the center of thicker sections. And microshrinkage is even finer porosity, usually occurring between the dendrite arms, the tree-like crystals, as they grow during solidification. It's often only visible under a microscope but can significantly reduce mechanical properties.
Shrinkage sounds like a major challenge.
It's one of the fundamental challenges in casting. Another critical defect related to solidification stresses is a hot tear, also called a crack or hot cracks.
Tearing while it's still hot.
Exactly. These are ruptures or cracks that form in the casting, either during the final stages of solidification or just below the solidus temperature while the metal is still very hot and weak. They're caused by tensile stresses that build up as the casting tries to contract, but is restrained by the mold or core or by uneven cooling rates. Hot tears often have ragged, oxidized surfaces because they formed at high temperature. Similar are contraction cracks or shrinkage cracks, which might form slightly later after solidification due to restriction during cooling and contraction.
Both types of cracks sound very bad for integrity.
They are major defects, often leading to scrapping the part. Then there are defects related more to the mold itself or how it was assembled. Flash is that thin web or fin of excess metal that squeezes out at the parting line between the cope and drag halves of the mold, or around cores. It happens if the mold halves don't fit together tightly or if core prints, the seats for the cores, aren't accurate.
Extra metal sticking out.
Right. Mold shift is more serious. It's when the cope and drag halves are misaligned relative to each other, causing a step or offset in the final casting dimensions across the parting line.
So the two halves didn't line up right.
Correct. Sag is a defect where a section of the casting is thinner than intended, usually because the cope top half of the sand mold, or maybe a large core, sagged downwards under its own weight or due to metal pressure before solidification was complete. Conversely, a swell is where a section is thicker than intended because the molten metal pressure actually pushed the sand mold wall outwards.
Sagging down or swelling out, mold stability issues.
Yes. Another surface issue is burned-on sand. Despite the name, it's usually not about burning. It's when the molten metal actually penetrates into the spaces between the sand grains of the mold wall, mechanically locking sand onto the casting surface. This results in a rough, tenacious layer of mixed sand and metal that's very difficult to clean off.
Metal soaking into the sand.
Kind of. An open grain structure refers to a condition where the casting, when cut or fractured, looks unusually coarse-grained and porous, often indicating underlying microshrinkage or gas porosity. A runout is a critical failure during pouring, where the mold fails to fill completely because molten metal leaks or drains out through a crack in the mold or a poorly sealed joint. And finally, you always worry about contamination or impurity. These are unwanted, deleterious elements that get into the alloy unintentionally, maybe from dirty scrap metal, furnace linings, or improper handling. Even small amounts can drastically affect the metal's properties or casting behavior.
That's a whole rogues gallery of potential casting problems.
Okay.
Okay, let's unpack this further. It sounds like technology isn't just for detecting problems after the fact with NDT, but it's also crucial for preventing these defects from the start and ensuring extreme precision throughout the entire design and manufacturing process. It seems like a full-circle approach now.
It absolutely is. Modern metallurgy and manufacturing are now deeply intertwined with powerful digital tools and automation, allowing for unprecedented levels of precision, simulation, process control, and quality assurance right from the initial concept.
Like using computers for design.
Exactly. It starts with CAD, computer-aided design. Engineers create highly detailed 3D models of parts with incredible geometric accuracy. These CAD models are the foundation.
And then you can test them digitally.
Yes. That's where CAE, computer-aided engineering, comes in. Using the CAD model, engineers can perform sophisticated simulations before making anything physically. A prime example is finite element analysis, FEA.
FEA? What's that?
FEA is a powerful computerized numerical technique. It breaks the complex geometry of the part down into thousands or millions of small, simple elements, like tiny bricks or pyramids. The computer then solves equations for each element to predict how the entire part will behave under various conditions like stress, strain, vibration, or heat flow. Engineers use FEA extensively to analyze stress distributions, predict deflection, optimize designs for strength and weight, and identify potential weak spots before committing to manufacturing.
So you can find problems on the computer first.
Precisely. For casting, CAE tools can simulate mold filling, how the molten metal flows into the cavity, and solidification. This helps engineers design the gating system and risers optimally to avoid defects like cold shuts, porosity, or shrinkage voids. It saves immense amounts of time and money compared to trial and error on the foundry floor.
And the computers control the actual making of the part.
Often, yes. CAM, computer-aided manufacturing, involves using software to translate the CAD design data into instructions for manufacturing equipment. And CNC, computer numerical controlled machine tools, are the machines themselves, lathes, mills, grinders, etc., that follow these computer-generated instructions with incredible precision and repeatability to cut, drill, or shape the metal part to the exact specifications.
So a computer's designing, simulating, and machining.
It's a seamless digital thread in many cases. We also use technology for rapid prototyping. The stereolithography apparatus, SLA, is a type of 3D printer. It uses CAD data to build physical models or patterns layer by layer, usually from a photosensitive liquid plastic resin cured by a laser. This allows engineers to quickly create tangible prototypes for design verification or even patterns for investment casting.
Holding a model of the design quickly.
Exactly. And for verifying the dimensions of the final manufactured parts, we use automated inspection equipment like the CMM, coordinate measuring machine. This machine uses a probe to touch multiple points on the part's surface, precisely measuring its geometry in 3D space and comparing it to the original CAD model specifications to ensure it's within tolerance.
Checking the final product automatically.
Yes, and the whole process is often managed using principles like simultaneous engineering or concurrent engineering. This is a collaborative approach where designers, manufacturing engineers, materials experts, and even suppliers work together concurrently from the very beginning of the project rather than sequentially. Design first, then figure out how to make it.
Everyone working together from the start.
Right. This drastically reduces development time, catches potential manufacturing problems early, optimizes the design for producibility and cost, and ultimately results in a better, more efficient part. It breaks down the traditional over-the-wall approach.
Makes sense. And you mentioned tolerance. How is precision formally defined and controlled?
Precision is codified through rigorous systems of measurement, standards, and tolerances. Tolerance, or allowance, is simply the total permissible variation of a size or dimension from its specified nominal value. No manufacturing process is perfectly exact, so tolerances define the acceptable range.
How much wiggle room you have?
Essentially, yes. Dimensional tolerance grades, like the ISO system, provide standardized levels of tolerance tightness, allowing clear communication of accuracy requirements across different companies and countries. Profile tolerances are a more complex part of geometric dimensioning and tolerancing, GD&T. They define a 3D tolerance zone around a theoretically perfect profile or surface, controlling its form, orientation, and location simultaneously. It's crucial for ensuring complex shapes fit and function correctly.
Controlling the shape, not just the size.
Exactly. And terms like machine allowance, finish allowance, or stock allowance all refer to the extra amount of material intentionally left on a rough, casting, forging, or pre-machined part. This extra stock allows for subsequent machining operations to remove surface imperfections and achieve the final precise dimensions and desired surface finish.
Leaving material for the final cuts.
Precisely. And underpinning all of this, the material specifications, the testing methods, the tolerances, the quality procedures, are standards developed by influential organizations. Think of ASTM International, American Society for Testing Materials, ASM International, the Materials Information Society, NIST, the U.S. National Institute of Standards and Technology, formerly NBS, ISO, the International Organization for Standardization, and military specifications like MIL-LSTD. These standards ensure consistency, quality, safety, and interoperability of materials and products across industries and around the globe.
So a whole infrastructure of standards keeping everything consistent.
It's absolutely essential for modern manufacturing and trade.
So bringing this all together, what does this all mean in the grand scheme of things? It sounds like an incredible fusion of pure science, deep engineering principles, and incredibly powerful digital tools, all converging to create and perfect the very materials that build our modern world, shaping our reality in ways we probably rarely stop to appreciate.
It truly is. If you step back and look at the journey from understanding the fundamental behavior of electrons and atoms in a crystal lattice,
Right, basic science,
to predicting how those atoms will rearrange during complex phase transformations under heat, to developing alloys with precisely tailored compositions, to designing intricate casting processes and simulating fluid flow, to controlling heat treatments with pinpoint accuracy, to employing sophisticated NDT methods to guarantee internal soundness, and finally using advanced machining and metrology to achieve micron-level precision.
It covers so many fields.
It does. The world of metals is really a microcosm of human ingenuity applied to materials. It's about leveraging profound scientific knowledge to control processes happening at the atomic and microscopic scale, and then scaling that control up reliably to macroscopic production. It's all geared towards ensuring the reliability, performance, safety, and longevity of countless products and structures, from the tiniest electronic connector to the largest bridge span or power generator. Every metallic object we use really does tell an incredible story of science and engineering.
Wow, what a journey that was. We started with what, on the surface, seemed like just a simple glossary of terms.
Yeah.
But this deep dive has profoundly shown us how those seemingly simple definitions unlock such an intricate, detailed, and profound understanding of material science, manufacturing processes, and even the complex ways materials could eventually fail. It's like each term we discussed was a key, wasn't it? Opening up a new chamber of knowledge, leading us step by step towards a comprehensive, interconnected understanding of this incredibly complex, yet absolutely foundational field.
Absolutely. I think this deep dive has really highlighted that every single term we've touched upon, from alloy right at the start to yield strength, fatigue, quenching, microstructure, NDT, FEA, is not just an isolated piece of jargon.
No, they're all linked.
They are all crucial pieces of a vast interconnected puzzle. Each term really is a key to understanding a specific property, a particular process, a potential benefit, or a potential problem in the world of metallic materials. It reinforces that these aren't just words on a page. They represent a holistic system of knowledge.
The system that lets us do amazing things.
Exactly. A system that allows us to design, create, and utilize metals with remarkable precision and confidence, ultimately ensuring the safety, efficiency, and longevity of almost everything humans build. And thinking about that interconnectedness, well, this raises an important question.
And that question, that final thought for you, our listener, is this. The next time you pick up any metal object, whether it's something as simple as a spoon in your kitchen drawer, or a critical part in your car's engine, maybe a cherished piece of jewelry, or even a tiny, almost invisible component deep inside your phone, take just a moment. How many of these hidden properties, these intricate processes of alloying, casting, forging, heat treatment, finishing, and meticulous quality control were involved in bringing that specific object into existence? How might those engineered characteristics affect its lifespan, its strength, its resistance to wear, or even how it might eventually reach the end of its useful life?
And maybe take it one step further.
How does this deep dive into just one seemingly niche area, the hidden world of metals, open your eyes to the astonishing, often unseen complexities inherent in all the materials, the plastics, ceramics, composites, glasses that surround you and shape your world every single day? We hope it sparks your curiosity to look closer and perhaps explore even further.